Hi guys, welcome back. It's time for another lesson. Today's lesson is about Faraday's law and Lenz's rule. So the main idea is that up until now we've had electric fields created by charges and magnetic fields created by currents. But we're about to encounter a new type of field generation mechanism, and that is a changing magnetic flux. But the type of field that a changing magnetic flux creates is not the same as a field produced by charges. So let's look at that. It's actually a curly electric field. It's an electric field that wraps around in a fashion similar to the way a magnetic field wraps around a current source. The electric field wraps around a changing magnetic flux. What is magnetic flux? Well, magnetic flux is an important idea that we need to master in order to be able to compute the creation of these curly electric fields. But the good news is it's very much like calculating electric flux. You simply take the dot product of the magnetic field with the normal unit vector, a unit vector normal to the surface, and multiply by the magnitude of the area of the little patch that the magnetic field pierces, of the surface that the magnetic field pierces. And then you add up the flux through each of those little patches, and you get the flux through the entire surface. So the mechanism or the mechanics of doing that are very similar to calculating electric flux, which we already know how to do from Gauss's law. In the end, you get a picture of a curly electric field wrapping around an increasing magnetic flux in a very similar way that the magnetic field wraps around a current. Now notice there's a notation on this figure that says the current is increasing. That implies that the magnetic field is changing, and that is what produces the changing magnetic flux that generates the curly electric field. It turns out the curly electric field is proportional to the rate of change of the flux, not to the flux itself. The other thing is that getting the direction of the electric field correct is tricky sometimes. If the magnetic field is changing, it turns out you can relate it directly to the rate of change of the magnetic field. But there are times when the flux is changing, but the magnetic field is not. You notice that the flux has to do with the area and the dot product of the normal vector with the magnetic field. You can have a constant magnetic field, but a changing area or a changing normal, and get a changing flux without having the magnetic field change. And in those cases, it turns out the easiest way to get the direction of the electric field identified correctly is to use something called Lenz's rule, which we'll get to here in a minute. Let's go back to the notion of a curly electric field. The idea is a changing magnetic field produces a curly electric field. The rule that we need to get that curly electric field is to compute the EMF. The EMF, as always, is computed as the line integral of the electric field. Remember back at the bubble diagram, to get from electric field to potential, we had to go E dot dl. Well, now to get EMF, it's the same integral, E dot dl. Excuse me. I want to look at this picture and notice the similarity with the picture we had for current producing a curly magnetic field. And in the process, we evaluated the line integral of magnetic field in Ampere's law. And the calculation was quite easy. We'd pick a path where the magnetic field was constant in magnitude and parallel to the path everywhere. In other words, in this case, there would be a circular path concentric with the current. And the integral just became the path length times the magnetic field, B times 2 pi r. In the picture on the left, we have a change in flux producing a curly electric field, and the EMF is the integral of E dot dl. But if you pick a path where the electric field is constant in magnitude, and always parallel to the path, in other words, a concentric circle with the solenoid in this case, the integral comes out exactly the same. The good news is we'll always choose paths for which this integral is easy to compute, and that's going to be beneficial when it comes time to actually doing the calculation. All right, let's look at magnetic flux. The idea here is that, as I said, you take the dot product of B and n hat and multiply by the area. Let's do an example just to sort of test things out. The flux is going to be the product of the area, but the area is 0.15 meters times 0.1 meters. Then I got to multiply by the magnetic field magnitude, which is 6 Tesla, and then by the cosine of 30 degrees, which is 0.866. If I multiply all that together, I get 0.078 Tesla meters squared. So flux comes out in units of magnetic field times area, or Tesla meters squared. We've got all the pieces now we need to actually state Faraday's law. And the way I remember Faraday's law is simply the EMF is equal to the rate of change of the flux in magnitude. There's a minus sign there, and the way I think of it is the minus sign helps us remember to use Lenz's rule to sort out the sign. So the EMF, of course, is simply the integral of E dot dl around the loop. The flux is the integral of B dot n hat dA. What about the rate of change? What's that going to get us? Well, that's going to be a simple d by dt, the time derivative of the flux. And of course, equals minus is just equals minus. So you put all that together, and you get Faraday's law. It looks like a terrible mathematical, nightmare, but really it's not that bad. It just says the EMF is minus the rate of change of the flux. Let's look at Lenz's rule. Lenz's rule is another way to say you can't fool Mother Nature, or there's no such thing as a free lunch, or you don't get something for nothing. There's different ways to look at it, but let me describe for you the rule, and then we can talk about its consequences. First of all, let's take an example where we have a magnetic field and a solenoid, and the magnetic field is increasing with time, and as you can see, it's pointing out of the page. I want you to imagine, this is not real, but imagine there is a loop of wire concentric with the solenoid, and the idea is we want to estimate or guess or determine which way the current is going to flow in this imaginary wire that's concentric with the solenoid. Now the idea is Lenz's rule says that whatever you're doing to change the flux in the wire, the current that's induced in the wire as a result of that changing flux is going to create a field that opposes that change. So if you increase the field, it's going to produce a field to try to decrease the field. If you decrease the field, it's going to try to produce a field that increases the field. That's the essential idea. Now the reason that's important is if it worked the other way around. In other words, if you increase the field and you could induce a current that would also increase the field, then you could turn the knob, take your hands off, and the current in this coil could keep making the thing change. It could actually carry on without you, and in fact, ultimately you could deduce that it could create energy without any work. So that turns out to be a no-no, and in order to make nature behave reasonably, you have to have it work the other way around. In other words, if you make a change in flux, the induced EMF opposes that change. So Lenz's rule is that the current will flow in this imaginary wire in a direction to oppose the change in flux through the loop. So in this example, in order to oppose the increasing field in the solenoid, you want a field pointing into the page to oppose that increasing field. And to create a current into the page, of course, you need a field that's clockwise. Since the current has to be clockwise to oppose the field, then the electric field has to be clockwise. And if the electric field has to be clockwise, that has to be true whether the wire's there or not. And so you can get rid of the imaginary wire having successfully deduced the direction of the electric field. All right, let's look at an example and see how that works. Imagine I have a solenoid or something that creates a magnetic field into the page, but decreasing with time this time, so that initially the magnetic field is half a Tesla. A tenth of a second later, it's gotten down to 3/10 of a Tesla. It's got an area of a tenth of a square meter, and let's just, for the sake of argument, assume that the resistance of the wire is 5 ohms. Let's calculate the magnitude of the EMF. I don't want to worry about the sign right now because we'll use Lenz's rule to get that. Let's say the initial flux is half a Tesla times a tenth of a square meter. That's 0.05 Tesla meter squared. The final flux is 0.3 Tesla times a tenth of a meter. That's 0.03 Tesla meter squared. And the change in time is a tenth of a second. So the magnitude of the change in flux is 0.02 Tesla meters squared. The time is a tenth of a second, and so the rate of change of the flux in magnitude is 2/10 of a Tesla meter squared per second. Now the EMF is the rate of change of the flux. The magnitude of the EMF is the magnitude of the rate of change of flux. So that means we have an EMF of 2/10 of a volt. In other words, the 2/10 of a Tesla meter squared per second is the same thing as 2/10 of a volt. The current, therefore, is going to be 2/10 of a volt divided by 5 ohms, or 40 milliamps, 0.04 amperes. Now, let's look at Lenz's rule. The magnetic field is decreasing, so I want to oppose that decrease, so I need to produce a field in the same direction as the magnetic field is right now. The magnetic field is into the page. To make a field from the current in the wire into the page, I need it to be clockwise. So there we get that the current has to be a clockwise current, even though the magnetic field is decreasing with time and it's into the page. And that's the way it works. All right, we'll see you guys next time.